continuing with our analysis of fundamental weather measurements, we get air temperature, we get infrared surface temperature. One of the other very key measurements is solar radiation to any input. And for decades, the only instruments available were expensive black body pyranometers. Then silicon cell pyranometers became available. And I think we have some here. They're in the catalogs. Let's see if we got one sitting here. Well, this is close. This is actually a quantum sensor, but they're this size. They're tiny. And now silicon cell pyranometers are almost an order of magnitude cheaper than black body pyranometers. So all of us use silicon cell pyranometers on weather stations to get solar radiation for our Penman-Monteith models and everything else. And we just say, great, we've just saved a lot of money. But what I want to show you is the differences and the errors that you get with silicon cell pyranometers. And these are not widely appreciated. It's only our work comparing them rigorously back and forth that we've seen these things. This comes from the fact that black body pyranometers, and you look at them and there's a glass dome and a black disc, record all of the wavelength, all of the radiation over this whole solar spectrum. This is the entire solar spectrum and on a typical sunny day. They measure all of this. These are all giant bands of absorption of water vapor in the spectrum. Outside the atmosphere, it's a smooth curve. But silicon cell pyranometers subsample this spectra and predict the rest. And we do that all the time in science. We subsample things and then we predict the whole. And that's fine, but subsampling changes, the spectra changes with atmospheric humidity. So what I'll show you is the data on how does atmospheric humidity affect this spectra and how does it affect the accuracy of our silicon cell pyranometers. I don't know how many of these I need, but this curve, this will relate to the next talk in photosynthetic radiation. There's so many things you can see from this curve, and we made a refrigerator magnet. Nowadays, not everybody puts these on refrigerators, but I go around and people have these on their filing cabinets so they can see the curve. But here's a magnet you could pass around and take one, and don't put it. I have a disc, it might demagnetize it or it might change it. But this is just a curve showing this in a couple different units. Here's watts per meter squared. But what happens on cloudy days? So here's the whole spectrum as an introduction to radiation measurements. And radiation was what Apogee has cut its teeth on, or quantum sensors, and we're known as a radiation sensor company. That's the whole curve. Now we get photosynthetically active, which is, most people in this room have got 400 and 700 memorized. That's the range of wavelengths that cause photosynthesis. It's also really close to the range of wavelengths for human vision. And then finally down here, UV. There's times when we just want to measure this, but with pyranometers, we're measuring the whole thing. It's all thermal radiation. That's what drives the change of state of water from liquid to gas. So here's black body and silicon cell. Now, look at how this curve changes on a cloudy day. Atmospheric water vapor not only takes out these bands, but it greatly reduces these bands of radiation. If you measure the whole thing with the black body pyranometer, you accurately measure this. But if you're only subsampling it, look at this. this spectra is hardly changed in the short wavelengths on a cloudy day. It selectively shifts the wavelengths this direction. And this is the spectral response of a silicon cell, these smaller silicon cell pyranometers that we all use. Thanks. And it selectively measures this. It doesn't measure this. So what happens is they over measure on cloudy days because they're subsampling the part that's transmitted more. So how bad is this effect of oversampling? Almost 10%, depending on how much cloudy sky there is, but that's a big error on cloudy days. Let's take a look at a couple of cloudy days in here. Here happens to be 3 days when we had full sun, which is what these sensors are calibrated to, and then partly cloudy, and then a significantly cloudy here. And if you just look at this, it looks like the curves are really pretty close, the black body and silicon cell. But when you calculate the errors, almost none here, and it just gets bigger here. So here's where we're 9, 10, even times it's greater than a 10% error. You can, of course, correct for this if you know the effect and you know the fraction of clouds, but rarely do people do this. They just assume the silicon cell is correct at all times. So there's a bottom line, there's a humidity effect on this measurement. Here's the magnitude of the effect here. And again, they're accurate in full sun because they're calibrated to full sun. And this is a same thing, data ratio of clear sky to actual, and the error always goes high in these conditions. This is also probably a pretty good example of models. This is an average of these, but this should taper down to 0, and there's just a few data points. And if you fit this with the model, that red line is really not very representative up here because we don't have enough data to make that. But it's an example of how we take data and make a model out of it. But on severely cloudy days, or significantly cloudy days, it's a pretty big error from silicon cell pyranometers. The good news about this is the cost of black body pyranometers continues to come down. And because of these errors, that we've sold a silicon cell pyranometer for a long, long time. And we just tell people about these errors. But because of this, and because of the need to make accurate solar radiation measurements in all the days, Apogee has now developed a black body pyranometer that looks like this. And it doesn't have these kinds of errors because of the spectra that it measures. A second source of error among instruments is called cosine error, and that refers to how accurately does the sensor measure all the angles of radiation. You can put any light sensor out there and get some relative indication of light, but it is really difficult to calibrate it for light coming right straight down and have it also be accurate when the light comes in at a low angle. Or, same thing on a cloudy day where there's equal radiation from all angles, the sensor has to accurately integrate all those angles. So here's an example of low angle radiation, and coming into this, and that's why we call this cosine correction, because if it's coming in this angle, the sensor should read 500. It's not supposed to read 1,000, that's cosine correction. Does it really read 500 if it's at that angle? You have to get that correction with the optics of the sensor, and all radiation manufacturers work hard to get cosine correction, at least the ones selling what we call research grade instruments. There's plenty of pyranometers out there that are really cheap, and boy, they do a terrible job of this. I worry about people selling cheap instruments and getting the cosine really wrong. And if you know what you're doing, you can test this compared to a better instrument. But this cosine is one of the things that people forget when some lower cost manufacturers sometimes forget. So here's all the angles coming into this thing. This is a graph of the angle and the error. So in this case, this is a bunch of pyranometers and the standard deviations. The morning and evening are slightly different, so they're really close until we get out to 75 degrees, and then the errors get bigger. This means they're not as accurate at dawn and dusk for those measurements, but there's not very much radiation out here either. It's low light, so a 5% error in low light is not that big of an error in absolute terms. But you would like these instruments to be accurate all day long, and summer and winter. How about changing sun angles? We get summer angles in here, and then we get winter angles over here. If it's not cosine corrected, it can have a big seasonal error because they're typically calibrated for summer sunlight angles. So we specify these often by the error out here at 75 degrees. And this is an example of how companies write specifications too. How accurate are they out there? You can't just test one sensor. You got to take your entire pool of sensors with replicates, and you want to make sure your specification matches all your instruments, not just your best sensors. So we specify 5% at 75 degrees, and this is 2 times the standard deviation, which is 96% of the tested sensors. Stability. This is a characteristic of all instruments. How stable are they long term? And humidity companies have said everybody can build a humidity sensor and it's accurate on day 1. Now check it 2 years later, 3 years later. All sensors drift, but companies work hard to minimize that drift. So this is some tests of silicon pyranometers for long-term drift compared to high-end black body. Now, Kippenzonen sells very expensive high-end black bodies. This is on the roof of our building in Logan, Utah. Multiple replicate high-end instruments to get a very accurate reference point. And you can see there's 2 glass domes inside of these to make a primary standard instrument. So here's data. Now we don't show the 100 pyranometers next to these, but it's a big table of checking them. And this is some data that were compared. The mean change was only 0.1% per year. So on average, these are very stable. Man, it's a very hard number to even measure. You have to go 10 years before you even see a 1% drift. But there's some variability in these. So we had some that drifted as much as 1.8%. Now, oddly enough, some went up too. They don't always drift down. There's tiny changes in the optics that affect the stability of the instruments. So because of this, we write our spec at 2% a year drift. And that's all of the sensors should drift less than that. And even though the mean is less than 0.1% a year. And again, I talked about this accelerated aging before, but to really be sure you've got quality instruments, you need to check long-term stability. It's one of the troubles with new instruments. Everybody gets excited with new instruments. How much did the manufacturer test those for long-term stability? You can't put them in an environment for 10 years. You're depriving people of that new technology, but you can run accelerated aging tests to try and make them fail to get better confidence that they're going to work in a range of environments. The tropics and the cold places, warm places, that's a critical thing with research-grade instruments. Now, another little point on these, here's some frost. Now here we are in Sydney, you don't get frost here, right? But but you get dew, you get condensation here. And here was a morning where we had, cold morning, we had frost. And actually this might be a radiation frost, which we'll talk about in a little bit. But these two sensors right here are clear. That's hard to see. They're clear because they're heated. And with this little sensor, we can put a tiny little resistance heater in this and warm it up just slightly to keep condensation off the sensor and to keep dew off the sensor, which we call that occlusion of the optical path. If there's anything on that sensor, it's going to read incorrectly, and frost is huge. I got some pictures in here of snow on sensors. That's also huge. It blocks, it sits on the sensor. You can buy heaters for those primary standard pyranometers, but now we're talking $5,000 to $10,000 for one instrument that's heated and ventilated to make an accurate measurement, versus a few $100s for a tiny sensor that has a heater in it. So those heaters have helped quite a bit to help people make more accurate measurements in places that get condensation or in places that get snow and frost. Here's some example of snow, buried under snow here and above the snow there. It's also on a pedestal to keep it above so snow can't stick to it. Temperature affects radiation sensors. This is an example of comparative tests that we've done with LICOR silicon pyranometers and ours. There's a tiny temperature effect in here. Most research grade sensors, this is a small effect. Look at this, goes from -10 to +40, and the effect is only 1%. So again, for precision measurements, this is repeatable, so you can measure and correct for the temperature effect on the sensor. It depends on how accurate you need the solar radiation. This, I think this might be my last slide in this. And this, I think, are we going to talk about net radiation next?
No, we're talking about that first thing after lunch.
Okay, this relates to that. Remember how we subsampled the solar radiation? So we often want to know, turn them upside down and know reflected radiation from the ground. And that's net shortwave radiation. So we take a carefully calibrated silicon cell sensor and just turn it upside down, and we say, great, now we know incoming, and we'll subtract outgoing, and we have net shortwave radiation. That would be wrong, because this subsamples, you turn it upside down and the reflected radiation is different, and you can get significant errors if you turn this upside down to do reflected radiation. And here's the magnitude of the errors. 14% error over a grass canopy. You can see almost 20% errors. So you should never use a silicon cell pyranometer upside down to get reflected radiation. They're not calibrated for that. You have to go to a black body pyranometer, which doesn't have this source of radiation. These are so inexpensive. Hold your question. These are so inexpensive, everybody gets tempted to do this. And now, if you know this and you're confident in it, you could correct for it in software. But man, you get really nervous about all these fudge factors. Sometimes they can make measurements worse. So, yes?
What about if you use it in vertical position, like not horizontal? So you said it upside down, but if you have it 90 degrees.
Yeah, and that's how you carefully level these. They're on a leveling plate, so the standard position is perfectly vertical.
But it would be a big error if you use it vertical, like in a wall.
Oh, like this? Yeah, okay. Yes, there is. Same thing. Because you're not measuring the sky, it's reflected. The errors would be similar. to this because of we're subsampling and the spectra changes. Same thing as clouds. Yeah. I spent some time in this because lots of people use these this way, and you tell them not to, and they still do. And people don't read the owner's manual. They just, I like this sensor, and I'm gonna use it. No. This is something we've done a bunch of work on to characterize these errors and try and make people aware of them through workshops like this, through videos online. If you know what you're doing as a research scientist, you can often get away with a lower cost sensor because you know its limitations. But pretty often it's people that don't know what they're doing that get tempted to buy low cost sensors, and then they misuse them and they can have big errors. It's sad because you see it all too often. This, yeah, that's my last slide in this, helping us a little bit to get caught up on time. Here's the aspirated shield that we were talking about earlier. We didn't have that out here. Part of what we want to help you do is evaluate specifications of instruments. You don't need to overbuy expensive instruments, but if you understand the specs, sometimes you can get away with less. Often you can get away with less than the highest cost instruments if you really know what you're doing and the limitations of the sensors. Leveling is a big source of error. The sensors drift. They become unlevel. Boy, people don't check that often enough. And what if the sensor starts to tilt very slightly to the sun or away from the sun? You can quickly get big errors from leveling. So we spend a lot of time making really rigorous leveling mounts, and they all have a bubble level, but now you got to climb in your tower and look at that bubble level to see that it's staying level. Occlusion of the sensor, of the dome, is a problem. Some sensors that are flat trap debris, they trap water, they trap dew. That's an error. And of course you can clean the sensors, but how many of us do? We don't. And now they read 10% low. Maybe until you get a windstorm, or not a windstorm, a rainstorm, and it flushes the sensor clean. Sensors that have a dome top help a lot. The water is self-cleaning and the water tends to run off. So those dome tops help keep the sensor clean. Also helps keep it dry. That's another nemesis of all instrument manufacturers is moisture getting in their sensors, causing drift or even the sensor to fail. You hold your thought a second. Let me go back to this. There. If you look at high-end sensors, and now unfortunately we can't quite see them in this picture because these are all shielded and aspirated to get peak accuracy, but you see a little side port with desiccant in the port, and it's often designed to change color. So if water vapor gets inside the sensor, you change that. So we go to a conference. We've been going to this conference in Brussels each year, a world meteorological conference. Kippensonen doesn't have that little disc with desiccant anymore on their sensors. And doesn't that keep your sensor dry internally, keep this perfectly dry so you never have condensation? And they said the biggest source of leaks in our sensor was that port, that little desiccant port. And so we just took it out, and now we have a better sealing, and it's dry when it's manufactured, and we hope it's going to stay dry for many years. It's an interesting change in the development of sensors. They felt like taking that out help people make better measurements than leaving it in and making them go and change the desiccant in the sensor. Because of that, we've worked hard. We pot our sensors solid, so there's no, in the pyranometers, there's not airspace. So moisture can't get in and cause problems with the measurement. Yes, Ben?
I was just wondering what's causing the stability to deteriorate.
A couple things. The fundamental physics of the detector change. Solar panels degrade over time, and this is basically a solar panel on a silicon cell that's becoming less efficient at taking sunlight and making a voltage. Changes in the optical path, tiny changes in deterioration of the diffusing material over it that can become less transparent. Those are the biggest fundamental things. In black body pyranometers, it's changes in this black surface. Now, Mark just talked about emissivity. Boy, they work hard to make that emissivity as close to 1.00 as possible, but as that ages, it starts to turn gray. And if it gets from 1.00 to 0.99, well, there's a 1% error. It's not fully absorbing the radiation. So really, all sensors have just the fundamental physics of aging of the detector. And solar radiation sensors are particularly subject to drift. Aging caused drift. Yes?
Do you get any oversampling in growth cabinets where it's measuring artificial light?
Yeah, did you say what happens with artificial light?
Yeah. Do you get any oversampling?
You bet you do. These are calibrated for sunlight based on that first slide. So now if you want it, then lots of people do this. They put them under electric lights, which have a very different spectra than sunlight. So silicon pyranometers can be way off with, 50% errors under electric lights because of the change in the spectra.
What about ones specifically calibrated?
Yes, exactly. It's possible to calibrate them, and they're fine. As long as you don't have a mix of sunlight and electric. But yes, they just need to be calibrated against a black body pyranometer for that light source. And then they're fine because you know the spectra and you can subsample and predict all of it. I think this is all I want to say about pyranometers and measurement of solar radiation. When we use the Penman Monteith for all sorts of things. We don't have any sensors to measure transpiration. We don't have any sensors to measure evaporation. Those are parameters that are fundamental to everything we do, and we got to predict them. We got to measure other things and predict them. So how accurate are the inputs to the models? Even though the models might be terrific, the inputs have errors, then the end result has errors too. I want to say one other thing that's not on the list, but I'll use this sensor as an example. The cable leading to sensors, different companies use different cables. You've got to get the signal from the sensor to the data logger, and higher quality sensors have higher quality cables coming out of them. So that usually people write specifications for the cable, and the first dead obvious one is you want this thing to be as waterproof as possible, so moisture starts to get in this. The signal, even though this is perfect, it's not getting accurately to the data logger. The other specification that's good to look for in sensors is shielding for electromagnetic radiation, and that's just wrapped with tinfoil and grounded at the other end so that you don't get electrical interference. And inside in greenhouses, this can be a particular problem if they're near fluorescent lights, if they're near equipment. You get electromagnetic noise picked up by the cable, so we shield them. That further minimizes any antenna effect of the sensor, and so the signal gets cleanly and clearly back to the detector. So it's shielded, twisted pair cable is the highest quality cable you can get to get the signal back to the detector. Now, not in the recent past, we used analog sensors. They took an environmental change, they make a voltage, you measure the voltage at the data logger and you convert it to our units that we want. Sensors are rapidly changing to digital sensors. So we have microprocessors in the sensors, so the measurement is made right in the head of the sensor and a digital signal is sent back to the data logger. So all companies are moving to more digital sensors. It changes the nature of the data logger that you measure it with, changes this whole thing because of a digital signal. That's generally a good thing, and the cost of that technology is coming down with digital sensors. The three big signals are SDI 12, serial digital interface 12, is common in sensors. Modbus is a second common one, and now USB. This one happens to be a USB port, no data logger needed. You buy the sensors and plug it into your laptop, and then you use the software and you can show the results on the screen. So the interface is changing fast in sensors, and the nature of the meter that you use to the sensor is changing because of that. It used to be digital sensors were quite a bit more expensive, but now that's much less true. And in general, digital sensors are better because of this signal effect. It's easier to send a digital signal over, not easier, it's more accurate to send a digital signal over a wire than an analog signal, and puts the burden of measurement right in the sensor head. I don't know if have you seen these options in sensors? It's really just in the last few years that more digital sensors have become available. And they're the same sensors, same optics, it's just a little microprocessor in the head. Okay, I'll stop here and turn this back over to Mark.